Hello. So I'm making this video after almost a week. I hope you have gotten time to look at the earlier videos that I have uploaded in the last week of September. So up till that point of time, we have covered definition of expectation for real valued random variables and some of the um, initial properties like up to 1 and 3 we have covered. 2 we have not yet spoken about, but 1 and 3 we have spoken. The proof is the proof of the property 3 I have actually written down quite elaborately in the doc file, and here the hints is given using a slightly different approach, but if you look at that doc file, so it doesn't require really this property 2. So I'd suggest you look at the doc file for which I made the video. And so what we know by now is that for any real valued random variable, if expectation of x plus or expectation of x minus one of them is finite, then the expectation is defined like this, and it may be plus infinity and minus infinity. However, if both happens to be finite, then this difference is a real number, and that we call the expectation of x. Now if we take the collection of all real valued random variables for which expectations are finite, then we get a space that we call the L1 space, and then that space is a real linear space. That is what we have proven. Real linear space meaning that if you take any two L1 random variable and take their linear combination, then there again L1 and the expectation of the sum is the sum of their expected, or a linear expectation of the linear combination is the linear combination of the expectation. There are two ways of proving it. One I have that proved in the previous presentation, and the one we can talk about it later, that is using convergence theorems. Anyway, so now suppose we can also there I have also mentioned to you that just for any real valued random variable x square is a non-negative valued random variable, so x square is always defined. Now if ex square happens to be finite, then we call them square integrable random variable or L2 random variables. Now in that case there is this inequality. This is called the Chebychev's inequality. And now what does that say? Probability of mod of x minus expectation of mod x greater than epsilon is less than equal to variance of x by epsilon square. Now this is something to be honest maybe a bit advanced for you at this stage, because variance of x we have not yet defined. We'll get to that, but we can for a moment just appreciate it that see, whatever may be, first of all, that if ex square is finite, then I will prove to you then expectation of x mod x is also finite. So in fact there is an inequality that I am going to write over here. Let me make it times Roman, and so I am working with the 816 font. That should be enough. So e of x square, that cannot be more than, so I have got, so if e of x square is finite, if e of x square is finite, x is a square integrable or L2 random variable, in that case expectation of mod x is a non-negative valued random variable, so it's always defined, is also finite. In fact, so now we have this relation, expectation of mod x square. So if I take the square of the expectation of modulus, that cannot exceed this copy. I think I have mentioned this. This is CS inequality or Holder's inequality, Cauchy-Schwarz inequality, or some people also called it Holder's inequality. So really, you may recall, you must have seen this inequality, right, in Riemann integration theory, and that if I have an integral a to b, suppose if a real valued continuous, suppose I have a real valued function that is square integrable, then integrable a to b modulus dy. I'm sure you must have seen this. This is a very famous inequality. So I don't need the modulus here anymore. Why? Because I am going to do this. Insert equation f square. So provided, of course, this is finite. So this is an inequality similar to this. Provided this f is Riemann integrable, or f square is Riemann integrable, to be more precise. So this is an inequality similar to this, and in that case, if x is square integrable, define variance of x equal to this difference, because this difference ex square minus expectation of x whole square, and okay, not exactly this difference, but you will understand in a minute. Copy, this is equal to ex square minus, I'll simply take not modulus, but I'll just remove the modulus, that expectation of mod x whole square. Okay, so this will be the variance of x. Variance of x as follows. Now you see here, now this difference is non-negative. Why? Because, recall, of course, recall this. Now, this is number 1, and also recall another thing, which is that mode of expectation of x, this is a non-negative number, this cannot be more than expectation of mode of x. So you see, that's the point. So if I take the so if x is square integrable, then expectation of mod x is finite. So expectation of x is finite, and also if you take, now these are non-negative numbers. So if a and b are two non-negative number, a is less than b, then a square is less, cannot be more than, so a square is less than equal to b square. So by that logic, square of this expectation is less than equal to square of the modulus expectation by the CS inequality. So you see, so the ex square can never be less than expectation of x whole square. Now this we call the variance of x, and now with little bit of algebra, it turns out to be expectation of x minus expectation of mod x whole square. Now generally in books you will see that this definition of variance is given first and then this is introduced, but here we have introduced from the other point of view, because for a simple reason that if the random variable is not square integrable, we cannot even talk about variance. Why? Because not only this if this is not square integrable, then this is not finite. Okay, but there may be something more complicated going on, that expectation of x, if x is any real valued random variable, expectation of x may not even exist. So once ex square is finite, really the CS inequality ensures that expectation of mod x is finite, and that in turn ensures with this property that expectation of x not only exists but this is a finite number, so you can add and subtract from it safely. So now if you have ex square that is finite, then this part is also finite, and this inequality is ensuring that this is a non-negative finite number. And now this with a little bit of algebra turns out to be expectation of x minus expectation of x whole square. So interpretation of variance is that if you look at the deviation from the mean, expectation of x is called the mean, and it is if you take the square of that, a square deviation from the mean, and then look at its average value. So it is a measure of dispersion, in the sense that if this quantity is large, that means some of the values of x are far away from the mean, and if this value is 0, then what does it imply? So variance of x equal to 0 implies what? That I will leave it for you. Implies dash. So fill up the gaps. Recall that this is a non-negative number. If this expectation of a non-negative number is 0, then you know the only result is probability x equal to 0 is 1. So that means x equal to expectation of x equal to 1. That means this expectation is, then this random variable is like a constant. So when variance is small, then the values of x fluctuates less. Extreme case is that when variance of x is 0, that means then variance is like a constant, it does not vary at all. When variance is not finite, that means there are some large values with non-negligible probabilities. That means that there is a non-negligible probability that a random variable can take arbitrarily large value. So we'll talk about this when talk about heavy tails, but as of now, so let us understand this much. Now I come back to the Chebychev's inequality. Now, so you see that I am starting with square integrable random variable. So all these things are finite. Expectation of mod is finite, and so is expectation of x. So now I am interested in how much the probability that x deviates from its average value. So suppose the x represents the price of a stock. So it is the, now the stock price varies every day depending upon